Hello there, welcome back to our channel, and we are going to analyze this circuit step by step. So what you see on your screen, we have an amplifier, which is a differential amplifier, or it's a dual input amplifier. It is also called as difference amplifier, or popularly known as operational amplifier. So the gain of this amplifier is indicated by AOL, which is an open loop gain. So remember, it is an open loop gain of the amplifier. For a practical amplifier by the manufacturers, the range of this AOL is approximately 10 to the power 5 to 10 to the power 7. So it's huge. So now let's analyze how having a very high open loop gain helps us to improve the performance of the circuit when we have a closed loop around the circuit. And when you close the loop, that is when you use the negative feedback, then another gain is established in the circuit. So that is called as ACL, that is closed loop gain. And we are going to see what is that gain. So what you see, it has two inputs, inverting and that is non-inverting. And let's call it as a V1, let's call it as a V2. And the operation of the circuit, that is UA, or we also call as output, will be given as gain times VID. And VID is the difference between the two inputs. You take a mod of it, so that's an absolute sign. So difference can be positive or the negative, so you take a mod of it. So you write here, that is your gain is multiplied, or the difference between the two inputs is multiplied by the gain to give you desired output. Now, when you have a negative feedback used in the circuit, then this gain is obviously ACL. When you don't have a feedback, such as the case when you use the amplifier as a comparator, where the output is switched between the two saturated levels, as we've seen in earlier modules. So if you are new to this channel, refer back to those modules on comparator, operational amplifier as a comparator. So in that case, you will write VO would be AD, that is the differential gain, or rather you would say that's an open loop gain multiplied by VID. Okay, so that's when you don't have a feedback. This is when you have a feedback. So where is the feedback in this circuit? So you see, so I repeat again, the portion of the output is being fed back to the input, and specifically to the negative pin or negative input of the amplifier. So therefore we say this amplifier has a negative feedback. So let me write it here. Okay, because we are feeding the output back to. And with that said, so let's analyze this circuit again. So this is V1, this is your V2. AOL is the open loop gain, which is in the range of 10 to the power 5 to 10 to the power 7 approximately. So it's very high. And we'll say how having such a high gain helps us to simplify the analysis of the circuit. So now this is UE minus and UE plus. So rather we would say the external input, let's say this is called as the input applied to the negative pin and input applied to the positive pin. We can also represent them as VA and this would be VB. And then you use the R1, in the first branch, then you use the R3 here, and then you have R4 right here. And the negative feedback is provided with the help of resistor R2. And here is your output UA, or you can also call it as a VO. Now let us analyze this circuit. So how this circuit work, and we want to have the expression for the output signal. So we say that there is a externally applied signal, so therefore the current will flow through that as indicated here. That current we call it is I1. This current again will be called as I2. Now this I1 is flowing through the resistor R1, and I2 is flowing through the resistor R3, and therefore also R4. So what you would like to do is apply at this node, which is small v1, this is small v2, these two nodes. We will apply the KCL, that is Kirchhoff's current law, at this node. So at node v1, apply KCL. That gives us to write the analysis. So input current I1 would be given as VA minus V1 divided by R1. So that's the current coming inside into this node. And then we say that there is this current component and there is this current component. The same current gets splitted into two parts, assuming the input impedance or the differential input impedance RID of the operational amplifier is very large. Ideally, it is infinite. Okay, so we say that no current can enter to inside the operational amplifier or difference amplifier, whether through the negative pin or through the positive pin. So we are basically doing the approximate analysis here. Now with saying that the IN, that is the current trying to enter into the negative pin, is approximately 0, and here also IP, that is the current trying to enter to the positive pin of the op-amp or difference amplifier, is also equal to 0. Now this current would be called as let's say we say that this current which is coming trying to go through R2, let's call it as a IF, because that's the feedback branch. So we say that the incoming current is equal to outgoing current. So therefore we'll write V1 minus VO divided by R2. That is the current. So here essentially you are saying I1 is equal to IF. So that's your circuit right here. And then you actually can get the expression for the input and the output. Now, while doing this analysis, we have assumed that we have short-circuited the external voltage source VB. It means we have assumed here that VB is equal to 0 while performing this analysis at with the VA active and VB is deactive. Okay, and now we can come back to equation 1, and then we try to analyze, get the expression for the output here. So what you would like to do is simple. We say that this would be, let's say, VA divided by R1 minus V1 divided by R1. So equal to V1 divided by R2 minus VO divided by R2. So that is how you actually can see that. Now we want to get the expression of output here, or the gain, VO over VA. So how would you like to do that? So we can We can also write this like VA minus V1 divided by R1, and we multiply it by R2, and here the R1 can be taken here, so it would be R1 V1 minus VO, and then we just simplify that, so it would be VA R2 minus V1 R2 divided equals to V1 R1 minus VO R1, and we just try to simplify it further. So we'll say that VA R2 plus VO R1, and here V1 R1 plus V1 R2, then you say this would be like V1 R1 plus R2, and here VA R2 plus VO R1. Oh, it's kind of difficult to analyze this circuit. Let me analyze it step by step. So since VB is equal to 0, there is this this node V2 is equal to 0, right? It is at the 0 potential. And we know that the VO over VID is equal to the gain. And we can also write the VO over the gain is equal to VID, right? So if the difference between the so if the gain is very, very high, if it is infinity, then VID is equal to 0, right? And it means the V1, and if we'll say that AOL is very high, then we'll say V1 is approximately equal to V2, and V2 is at 0 potential. Therefore, V1 is also at 0 potential. So essentially, this concept is called as virtual short, where the V2 and V1 are at the same potential. So now V1 is equal to 0, so we can plug in that value here. So V1 gets 0 here. So we'll say that VAR2 is equal to negative VO of RF. VA over VA, VO over VA will be minus R2 over R1. I have corrected the mistakes. There is no RF, and in fact it is R2, not the RF. Okay, so the look at the gain, that is our ratio of output divided by input, is R2 over R1, and this got possible when we said VB was 0 and only VA was in action. Now let's say VA is equal to 0 and VB is active. So with VA is, let me use a different color now. So with VA is equal to 0 and VB in place, VB active, we see that this current flows there through the R3, and now we are at this node. So the voltage V2, can be written by applying the voltage division rule, that is R4 times VB divided by R3 plus R4. So that's the voltage is coming here, the V2. Okay. And now we say that VA is equal to 0. So obviously you don't have I1 flowing. I1 is equal to 0 here now. Okay, and with the negative pin is connected to 0, the circuit will act as a non-inverting amplifier because the input is at the positive pin to the amplifier. In earlier case, the case here, all these expressions that we have written, we use the amplifier as an inverting amplifier because positive pin was connected to the ground. V2 was 0 in that time. And now the V1 is equal to 0. Okay. So remember this difference between the two signals and the two cases. So with the V2, we have this input, and we know that the inverting amplifier will look like this now. The negative pin is grounded because V1 is equal to 0, and V2 has a kind of circuit like this. So this is your VB, and that is your R3, that is your R4, and here is your V2. That voltage is this one. And the gain of this circuit, then we know that there is obviously a feedback, and you have like well, you say that this is your R1, and this is grounded, okay, and there is no current, and this is your R2 that is coming. So output here will be V2, that is the input voltage, multiplied by the gain, and the gain will be 1 plus R2 over R1. We know how the negative how the non-inverting amplifier works. We can also again apply this virtual short concept, and then the voltage at V2 appears at V1, and then apply the KCL and derive this expression. We'll reach here. So VO will be now R4 times VB divided by R3 plus R4. This is your input V2 multiplied by the gain factor R2 over R1. Right. So let's say this is the VO2, and that is your VO1. Okay. And the VO1 here can be written as VO1 would be negative R2 of R1 multiplied by VO. And the final output would be VO1 plus VO2. That is the output coming due to both inputs. So you can just write them. Negative of R2 over R1 times VA plus 1 plus R2 over R1 times R4 into VB divided by R4 plus R3. Now you choose appropriate values of the resistors, and then this final expression of output can further be simplified. Okay, so imagine you choose R3, R1 equal to R3, and R4 equal to R2, something like that. So with that combination, you can simplify and help that analysis. Okay, so hope you like this video. If you did so, click the like button, and you learned how to amplify the signals. And this is a simple difference amplifier.